Welcome. On behalf of the MODUS consortium, I would like to present you to the first screencast in the series of screencasts describing the functionality and usage of different parts of the MODUS toolset. During this screencast, we will present you the first version of the formal validation and verification block of the MODUS toolset. The scope of this presentation covers a simple scenario of creation of the model description using UML editor. We will briefly summarize creation of class diagrams, state machine and collaboration diagram, as they are necessary to obtain a model with behavioral properties that later can be simulated and verified against our assumption. This will be followed by presentation of the translation of the XML file containing the model into the description of the model in the Promella language. Finally, we will show how the model can be used for spin simulation and verification. Let's now introduce an environment that will be used during the formal model analysis. As all other MODUS toolset components, it is integrated with Eclipse IDE. Until now, it integrates Argo Eclipse plugin, Spin plugin, and finally MODUS Wizard, used for transformation between XMI and Promella, which is based on Hugo RT. Argo Eclipse is one of many available UML editors for Eclipse. We decided to use it as it was used by creators of Hugo RT, that is, the XMI to Promella translator used in the backend of the formal verification MODUS toolset block. This approach lowers the probability of incompatibility issues. Creation of UML diagrams in Argo Eclipse is essentially very similar to doing it using any other GUI-based UML editor. In a drag-and-drop fashion, we create all the necessary diagram components presenting the functionality of our system. For the purpose of this screencast, we prepared a simple model of two classes, ping and pong, exchanging the messages in continuous fashion. Once all the diagrams are ready, that is, the class diagram showing the two classes and their attributes and operations, the state machine diagrams presenting the behavior of the class elements, and finally the collaboration diagram presenting part of the game the ping and pong plays, we can proceed to the formal verification of the model. In order to do that, we need to export the diagram into XMI format, basically by export feature allowing the Argo Eclipse to create the XMI file. And in the navigator view, we have our XMI file. We would like to also mention that in order not to have too many states of the game, we limited the number of exchange messages to 4, which is visible on this state diagram, that the maximum number of ping messages or pong messages cannot exceed 4. With XMI file at hand, we are ready to perform the translation of the UML model into the formal model representation in Promela language. This will be done using MODUS verification and validation wizard that utilizes HugaRT, an open source translator of UML models to Promela models. In order to proceed with the translation, we should pre-select the file we want to translate, later choose File, New, Other, MODUS Wizards, MODUS VV Model Translation. Next. Due to pre-selection, the wizard contains information about model source and also prefills information about the outputs. Let's say we want to have an output in our main folder with this name using pre-selected HugaRT options, and we want to use HugaRT. By clicking Finish, retrigger HugaRT use, and we obtain the Promela representation of our model. With the obtained formal description of the system, we can proceed to the model checker. The model checker we are using is called Spin. Spin is a Promela interpreter, and in our case it's triggered by the Spin Eclipse plugin, which also contains possibility of configuration of certain spin properties. At the same time, it can be used for displaying the results of the simulation and verification. So coming back to Eclipse environment, we can configure different spin properties and options, like simulation style and seed values, but also verification properties, choosing correctness properties or some memory constraint, etc. Then we can perform a syntax check where we can see some warnings but no errors. Next, we can perform a simulation of our model where Spin is creating three processes: the init process, but also ping and pong. If one is interested in more details, it's possible to perform a more verbose simulation where we can see the states that particular parts of the model went through. Finally, we can perform verification of our simple model. This is simply obtained by clicking the Spin verification button, and the results presented in the console show us that for selected settings we have obtained 0 errors. Second part of this video will cover the case of RSL validation, where we will use UML to RSL translator to go from XMI model representation into the formal model description. So let's go back to the moment where we have XMI representation of the model and we want to obtain the formal model, but this time we want to get the RISE representation. Here again we'll use MODUS Wizard. We select the file we want to translate. After that, New, Other, MODUS Wizards, MODUS Formal Verification, Validation, Model Translation. Next. And we can see a number of options. We can either force the translation using Hugo, that is a translation to Promela, force the translation using UML to RSL that will allow us to obtain RISE model, or we can use a MODUS auto selection feature. For a model selected here, choosing this or this option will have the same result as the auto selection algorithm for the type diagram I have selected will use UML to RSL. Let's assume we want to use auto selection method. We click finish, and in one of the folders that is called auto location, we should observe the generated RSL files. These files correspond to different elements of our UML diagram, and they contain their description and RSL language. Since the diagram that was used for creation of these files didn't contain any behavioral data like state machines or collaboration diagrams, the user would have to fill this data within the file. Let's jump to a simple example where we already have put all the necessary information. We can see a simple RSL model that contains both the transition system and LTL assertions and a simple description of its components. You might have noticed that since RSL file is selected, we get some additional many buttons to perform the formal verification. In order to do that, first we need to obtain SAL representation of the selected file. We do it by pressing this SAL button. As you see, some additional files are created within the folder containing the model. With this at hand, we can perform a well-formedness check using the SWF button. The output is simply generated in the console, and we can see that the result of well-formed checking is OK. Finally, we can also check if the model contains deadlocks. And in the model we have showed you, there are no deadlocks, which is indicated by a message in the console. The final stage is the model checking. Here, for selected transition system and LTL assertion, we will obtain the model check. And we can see that the results of the model checking are successful. That is all in this screencast. We hope you enjoyed it, and thank you for watching.